Imagine two people in the void of space playing catch with a ball. When he throws the ball, the first person experiences a recoil because he passes momentum onto the ball. Similarly, when she receives it, the other person absorbs the motion of the ball and also experiences recoil. By throwing and catching the ball, the two individuals have repelled each other. They were motionless at first and are now in motion. If they continue to pass the ball, their speeds will increase each time, and they will move away from each other faster and faster. They behave as if they were experiencing a force. The action of the ball can be viewed as a force of repulsion. In nature, at the quantum scale, this phenomenon is at work between certain particles, such as electrons, which constantly exchange virtual photons. A virtual photon is a particle stemming from the laws of quantum physics, which can appear out of nothing provided it disappears fast enough such that we cannot detect it. A virtual photon has a certain energy, and the more energy it has, the shorter its lifetime. Therefore, the less energy a virtual photon has, the greater the distance it can travel. By exchanging virtual photons, electrons experience a repulsion, a force that pushes them away from each other, like the two people playing catch. This force is increasingly powerful as the distance between electrons shortens because the virtual photons then have less distance to travel and can thus be more energetic. Many other particles exchange virtual photons, and their tendency to interact in this way is called the electric charge. The electron has an electric charge of -1 e. E is the basic unit for electric charge. A particle will have a certain multiple of this elementary brick. Some objects interact more than a single electron. We can imagine an object containing two electrons and whose electric charge would be -2e. Moreover, some particles, like protons, interact with virtual photons in the opposite way. Their electric charge is positive. The charge of the proton, for instance, is +1e. Just like with two electrons, two positively charged particles repel each other. However, a negative particle and a positive particle attract each other. Charges of the same sign repel each other, while opposite charges attract. The electric field. To take into account all these interactions, we introduce the electric field. We can conceive of it as a sort of imaginary fabric. If we place an electron in the field, which is negatively charged, the field turns blue. However, if we place a proton, which is positively charged, the field turns red. If we drop new particles, they will escape from the areas which have the same color as them. A neutral particle without electric charge doesn't feel anything and moves in a straight line. A positive charge, such as a proton, will be repelled by red areas and attracted by blue areas. A negative charge, on the other hand, will be attracted by red and repelled by blue. Let's illustrate the electric field with several examples. Here is the field created by two electrons. We see that the central position between the electrons is in equilibrium. If we place a particle there, it would remain motionless, somewhat like a ball between two hills. Now, here is the field created by an electron and a proton. The two particles attract each other, as the electric field forms a bridge from one particle to the other. Finally, if we place a chain of electrons on one side and a chain of protons on the other side, we can create a uniform electric field in which a particle would always feel the same force. Doing so, we can make electrons move along an electric wire and thus create an electric current. The magnetic force. At this point, a disturbing phenomenon comes into play. Consider an electric wire consisting of a long chain of protons and electrons through which flows an electric current, which corresponds to the motion of electrons inside the wire. Imagine now that we leave an object a certain distance away from the wire, which carries a positive electric charge. According to what we saw earlier, each proton in the wire repels the apple, as their charges are both positive. At the same time, each electron attracts the apple with the same intensity. Overall, if we add up all these forces, they compensate each other, and the apple does not experience any net force. It remains motionless. Let us now throw the apple to the right. Strangely, we now observe that it is gradually repelled by the wire. While it is not subject to an electric force, the apple seems to be experiencing a mysterious force that pushes it away. This new force is very peculiar. It does not appear when the apple is motionless, but only when it is moving. Moreover, it seems to depend on the direction and the speed of the apple. This mysterious force, which appears when an electric charge moves around, is called the magnetic force. To understand its origin, we will have to review what special relativity teaches us. Before that, though, let's study the situation not from an outside point of view, but rather as it is perceived by the apple in its own frame of reference. From this point of view, it is not the apple which moves to the right, it is the wire that moves to the left. Now, according to special relativity, the faster an object moves, the more its length gets contracted in the direction of motion. In this reference frame, the protons in the wire are now in motion. They will thus get contracted along the direction of the wire. The protons come closer to each other. Conversely, the electrons appear to be moving more slowly because the entire wire is now moving to the left. They therefore get slightly stretched compared to the previous point of view and move away from each other. Overall, when we add up the forces acting on the apple from this point of view, they no longer cancel out. There are more positive charges, protons, than negative charges. Therefore, the wire exerts a repulsive force which pushes back the apple. The magnetic field. By considering special relativity, we see that the electric field of a charge gets distorted when it starts moving. This phenomenon involves the appearance of a new force, the magnetic force, which is, in fact, an electric force perceived from a different reference frame. Similarly to the electric field, we can summarize all these behaviors under another field, the magnetic field. When an electric charge moves, it creates a magnetic field around it, which can be represented as arrows revolving around the direction of motion. The magnetic force is a consequence of special relativity, and the behavior of the magnetic field is therefore rather strange. In a magnetic field, a stationary particle does not feel any force. On the other hand, a moving particle experiences a force whose strength depends on how perpendicularly the particle moves in relation to the magnetic field. This force tends to pull particles in circular trajectories, the size of which depends on their mass, their speed, the intensity of the field, and the electric charge. Although it is difficult to visualize, we can get some intuition of the magnetic field by considering the following experiment. We wind a wire on itself to form a long coil, and we apply an electric current to it. By moving inside the wire, each electron creates a small magnetic field around itself. Overall, these small magnetic fields add up and form a large-scale field, which loops around, exiting at one end and entering back through the other end. In this way, the coil behaves like a magnet, an object with magnetic north and south poles. We call this an electromagnet. The electromagnetic field, Maxwell's equations. To conclude, the electric and magnetic fields are inseparable, one is the origin of the other, and it is natural to unite them under a single concept, the electromagnetic field. The electromagnetic field behaves and evolves in a well-defined way, which can be summarized in 4 fundamental principles. We call these Maxwell's equations.